All right, for this part, we will be looking at static equilibrium. So static equilibrium is something we already went over in Newtonian dynamics. Um, Here we're going to be looking at more complete version of static equilibrium because we have now two conditions that must be satisfied for the object to be in static equilibrium. Not only the net force should be zero, also the net torque should be zero, which means that object cannot have any linear net force or any rotational net force. Basically, it cannot move in a translational or basically net translational force or basically rotational, forces. So it cannot rotate, but cannot move translationally. So for this one, then you can see, right, the applications are many, right? Buildings, dams, bridges, and any other structures, right? So they are basically have to be in a total static equilibrium. That means there have to be no rotation also involved. So this no net torque is now a requirement for those type of buildings. So for a rigid body in total equilibrium, there is no net torque about any point. That means our system cannot be rotating. So all the torques should be canceling, all the forces should be canceling. Okay, so that's the next few slides, the next few examples are going to be basically based on. In terms of, we are looking at the total static equilibrium problems where now we have two conditions satisfied. Condition one, the net force equals zero, which in a way can give us up to two equations, right? Net force in x direction equals zero, net force in a y direction equals zero. Then condition two, which is net torque equals zero. So you get basically one equation out of this because you get clockwise, counterclockwise can be combined in one equation. So in a way, you have now three equations. Equation one, net force in a x equals zero. Equation two, net force in a y equals zero. And equation three, net torque equals zero. We usually just keep it, two-dimensional here, plus the net torque. All right, so let's look at several examples. So here we have 120 centimeter wide sign hangs from a 5 kilogram, 200 centimeter long pole. A cable of negligible mass supports the end of the rod as shown. Um, what is the maximum mass of the sign if the maximum tension in the cable without breaking is 300 newtons? All right. So some of the important thing in this type of problems here is to identify your object of interest. That means which one is your object and what are the forces acting on this object. And our object is basically is this. So you have a pole, right? So 5 kilogram, 200 centimeter pole that has number of forces acting on it. So if I'm doing the free body diagram for this, for the pole, so there will be several, forces acting on it. But the idea here is all the forces should cancel each other, both in x direction and in a y direction. Also, there should be, no torque with respect to any of the axes. Okay, so let's first do the, free body diagram. So like, let's say, look at the forces. Well, one obvious one is the tension force, right? So here's the tension force. So input like this, here's a tension force, which is basically acting at this end of the pole. Well, there also, well, this pole has a mass and it has a length. So you can assume that all the mass of the pole concentrated at the center of mass, which is halfway, and the gravity acting on the pole at that position, which is basically somewhere over here, let's say. So there's this, the weight of the pole, right? Weight of the pole. Um, well, there's also a sign, yes, physics shop sign, which acting at sort of like two different positions. One is at the end, another one is right here. So then technically they are providing, two forces. So each one, since the sign connected to the pole by two tensions, so each tension from the sign is basically equal to half of its weight. So basically half of the weight of the sign, this one is half of the weight of the sign. You can see, right? Let me do it like this. Okay. And also the support point with the wall generally exerts two forces. One, there is a friction upward static friction. The other one is a normal force, like this. So you can see right there, quite a lot of forces acting on this pole. So then next step will be to the force table. So here we have tension, we have the static friction, normal force, weight of the pole. Then you can say that half of the weight of the sine, another half of the weight of the sine, because there are technically two different forces, right? And that's it for now. Let's say here's the net force, and I know it has to be zero because the system is in static equilibrium. All right, now the tension is a two-dimensional force, so I can break it down into components. So then this is Tx and this is Ty. And to get, sort of like the angle, right? So I need to then basically, sorry, this is Ty, this is Tx. I made a mistake. So I can use the, the fact that I'm given that this is 250 centimeters. From here to there, this is 200 centimeters, right? I can then use the trigonometry to find that angle theta, between them. So because then I can use this theta and break it down, the x component as Tx. Tx is basically T cosine theta, and Ty is T sine of theta. And I can also see that Tx is pointing to the left, so it's negative. Ty is pointing up, so it's positive. Static friction has no x component acting in a positive y direction. Normal force is acting in a positive x direction, has no y component. Weight of the pole acting in a negative direction, negative y direction. Then half of the, the weight of the sine, both are basically negative, like that. So I get equation 1, which is net force in the x direction. So this is normal force minus T cosine theta equals 0. Equation 2, then in a y direction, so I have T sine theta plus the static friction minus weight of the pole minus 1/2 weight of the sine minus 1/2 weight of the sine, then this is equals to 0. Okay. Now, remember, my goal here is to find the maximum mass of the sine. That means if I would find the weight of the sine, I can then calculate this. From here, one thing I can see here is that unfortunately I cannot do that because I don't know what the static friction or the normal forces are. I don't know those values. That's because we're not given the coefficient of static friction, that we can have for that pole and, a wall interaction. So we're kind of stuck with these two equations. But then there's also a third equation, which is the net torque, which should equal to 0. And then for the net torque, here's basically what I have. So think like this. So this is the pole. So I have then 3 forces acting on it. So here's a tension. Here's the half of the weight of the sine, right here, right? And here's the other 1/2 of the weight of the sine. Here's then weight of the pole. Then I have here's the normal force, and here's the static friction. So those are basically the forces acting. Okay. Now, in order now for me to get the net torque, well, first I need to know, okay, what is the axis of rotation? What is the pivot point? And here's the interesting part. Because your system is in static equilibrium, there is no pivot point. It's not rotating. So there is no true pivot point. There's no true axis of rotation. So what do? Well, we are free to choose any point we want to be our axis of rotation. That means I can take this point over here. I can take that point. I can take this point, or I can take that point, right? Any of those points are fine. But obviously, one of the things you want to do here is choose a point that is the most convenient. So for example, like let's say if I'm using my equation, so this will be torque, let's say, remember it's a net, the net torque is a vectors, right? So then it's torque due to the static friction. plus torque due to the normal force, plus torque due to the weight of the pole, plus torque due to the tension, then plus torque due to the first 1/2 weight of the sine, plus torque due to the second 1/2 of the weight of the sine, then equals to 0. Okay, so I have, 6 different, torques acting on it. But what I can do here is I can choose one point to be axis of rotation that can eliminate any force that's going through that axis of rotation. Remember, right? Any force going through the pivot point is 0. So think like this. If I choose this left end to be the axis of rotation or my pivot point, then it eliminates static friction and a normal force, and they don't exert any torque. And that's what I want, because I don't know any information about them. And I don't need to if I take that point to be my axis of rotation. So then my torque equation will be this. Net torque is equals to torque due to the weight of the pole plus torque due to the tension plus torque due to the weight of the sine, right? So 1/2 weight of the sine plus torque due to the other 1/2 weight of the sine. Again, I'm not combining them because they give me different torques with respect to the left end, right? Because their R's is different, right? So this first 1/2 weight of the sine is closer than the second one. So they give me different torques. So that's why I'm not combining them. So then this is equals to 0. And that's what I'm going to do right now. Taking that left end to be my axis of pivot point or axis of rotation, I'm going to first write in terms of weight of the pole. Well, weight of the pole is basically the torque, right? To the weight of the pole is the force magnitude, which is mass of the pole times g, then times its distance, which is half the length. So it's 0.1 meters or 1 meters actually, right? Because it's 100 centimeters. And I can see, right, if I'm doing the R and weight of the pole or half of the weight of the pole of the sines and things like that, all perpendicular to the radial line. So technically then sine of angles basically is sine of the 90 degrees 1 for them. That means this is this guy over here. So it's sine of 90 degrees. And I can see that weight of the pole going to give me sort of like, let's say, a negative, right? Clockwise, a rotation. So this guy here is negative. So then plus torque due to the tension. So the torque due to the tension here is the only one that actually giving me positive. And I can find using, again, tangent of theta equals 250 over 200. Then I can find this angle theta. So using that, I can get the theta equals to 51.3 degrees. Okay. And then say, all right, so for the torque of the tension is the tension magnitude. So basically, let me do it like this first. So it's tension times the distance, which is basically, 2 meters, and then times sine of 50, let's say sine of theta right now. Let me put it like that. So, and it's positive because it's going to give me counterclockwise rotation. Then minus, so let's go to this guy. The first, weight, half of the weight of the sine. So it's minus because it's going to give me clockwise rotation. So minus 1/2 mass of the sine times g. So this is its magnitude. Then the distance, and I can see it's given that, it's 80 centimeters from the left end, right? So it's basically 0.8 meters. Then sine of 90. Then minus, then the second weight of the sine. So same way, 1/2 mass of the sine times 9.8 times distance, and the distance here is 2 meters. And again, it's sine of 90, so I can just ignore that. So that all equals to 0. Right, so and you can see, right, all I have right now is that if I replace this mass of the pole with 5 kilograms and this G with the 9.8 and this tension here with the 300 newtons, the only thing I don't have is the mass of the sine. Everything else is basically given to me. So then I can solve for the mass of the sine, and it equals to roughly 31 kilograms. All right. That means mass of the sign is roughly 31 kilogram. And I use the net torque by choosing the pivot point to be where the pole connects with the wall, and it eliminates those static friction and a normal force. And then I have just only 4 forces applying torque, and I know basically everything that I need right now to just solve for the um, mass of the sign. Okay, so, and this is how you basically solve this type of problems. You first do your free body diagram, then you force table, then set up the equation for the net force in X and Y, right? So those 2 equations. And if you can solve whatever you want from those equations, fine. If not, then include the 3rd equation, which is for the net torque. Sometimes maybe starting with the net torque equation is easier. You might be able to just solve for the unknown directly from there. All right, here's another example. So this is also kind of like a typical example where we have a ladder leaning on a wall, right? And basically the friction from the wall and from the floor prevents it from, sliding. So it's in a static equilibrium. All right, so let's look at it. So you have a 3-meter long ladder leans against a frictionless wall. The coefficient of static friction between the ladder and the floor is 0.4. What is the minimum angle the ladder can make with the floor without slipping? Okay, so basically we need to pretty much find this, angle, that it makes um, with the floor without slipping. All right, so let me do my own free body diagram so I can kind of like explain as we go. All right, so let's say here's the ladder like this. All right, so it makes 2 points of contact, right? So one is right here with the wall, and another one right there. So for example, there is this normal force. So there are 2 normal forces, one from the floor, one from the wall. So okay, so here's one, let's call this N2, and here's another one, let's call this N1. And there's also 2 frictions, sorry, 1 friction, because it's a frictionless wall. If the wall is not frictionless, then there would have been another force, friction force from the wall. All right, so think like this. So if the ladder would be, let's say, slipping, right, it would be moving, let's say, to the right. So then the floor prevents it from that. So there's a friction force from the floor in this direction. Also, if let's say the wall was not frictionless, that there would have been a friction force like this from the wall. But we don't have this in this particular example. But you might see an example where there is a friction on a wall, right? And then that friction will be like upward, because otherwise the ladder will be let's say slipping downward, right? So it would have been preventing. Okay, so those are the 3 forces from those 2 contact points. But there's also another force, which is gravity acting on the ladder at the center of mass. You can see, right? So, and that's exactly halfway. So then we have this, let's say F of G, right, like this, right? So now those are the forces acting basically on our ladder, and the ladder obviously is the object of interest. So net force should be 0. So then we can write down in terms of our forces, force table, X component, Y component. So I have, all right, so let's say gravitational force, normal force 1, normal force 2, and then the static friction. Again, the net force should be 0, 0. You can see then the gravitational force is straight down. Normal force 1 is straight up. The normal force 2 is in a positive X direction, and static friction is a negative X direction. So you basically get something like this. All right, so equation 1 is then N2 minus F of S equals 0, and equation 2, N1 minus F of G equals 0. So basically we have this. That means in a way normal force 2 is equal to the static friction, And normal force 1 is equals to then, let's say mg, right? The weight. Remember, our goal is to find the angle that it will make. That means the ladder will make with the floor. That means we want to find what is this angle theta. Okay. Now, looking at these equations, right, I can't really solve for the angle theta because I don't have any information from here whether there's theta. I can even simplify with this a little bit because f of s equals then mu s times normal force 1, and this is equals to then mu s times mg. So this is kind of, as far as I can go from here. But then next I can use the equation 3, which is the net torque. Okay. And for this one, then I can choose any point to be my pivot point. Then I can then try to find some kind of information about the angle theta. Okay. So again, any point could be a good point for the pivot, but ideally you want to choose a point that eliminates as many forces as you can have. So your equation of the torque is just much simpler. So for example, if I choose this point right here to be my pivot point, then the torque due to the normal force 1 and due to the static friction, they're disappeared, they're gone. All right. That means what I can do from here is this. Our net torque now is going to be in terms of torque due to the normal force 2. And it's going to be negative because it's going to give us, with respect to that, sort of like a clockwise. And then plus torque due to the gravitational force, which kind of going to give us clockwise, counterclockwise. So then this is equals to 0. Then here what I'm going to use is that lever arm method. So that means if I kind of extend this normal force 2, right? So see, if I extend, then the direct closest distance from the pivot point to there, let's call this D2, or sorry, let's call this D1. Well, it is D2, so according to that. So let's call this D2. And then same thing I do for the gravitational force, go like this, and then this distance. So this distance I'm going to call this D1. Okay. That means it's negative N2 times D2, then plus, then mg times D1. And this is equals to 0. Then I can look at it in terms of, okay, so what is, let's say then D1? And what is, let's say, D2? Okay, so from here, again, using, let me kind of make this a little bit cleaner. For example, this is what we get. See, this is my theta. Okay, this is my theta. And my theta is for, let's say, this triangle. Let me make it in a, basically for this triangle, for the gravitational force, D1 is the adjacent, right? Then this distance, which is half of the L, is then basically becomes the hypotenuse. Okay, so then I can rearrange those and have a D1, which is the the x component or adjacent side. Remember, in terms of, let's say, cosine theta, right? Because cosine theta is adjacent over hypotenuse. So D1, which is the adjacent, will be, hypotenuse times cosine theta. That means this term basically becomes, so mg times 1/2 times the length times cosine theta. All right, minus, now let's look at this term. What is D2? Well, this theta is same as that theta, right? And in this case, then D2 basically becomes the opposite to that, let's say, to that angle. So then that basically becomes in terms of where the hypotenuse is the entire length of the ladder L, and then this becomes just basically N2 L sine of theta equals 0. All right, so that's basically what I end up with. And then I can say, all right, so then mg 1/2 L cosine theta equals N2L sine of theta, right? So I end up with that. And from here, I can see that I can pretty much even cancel the L's. I don't need that. And then I'm going to divide both sides by basically cosine theta. So if I do that, this will go away. And on the right side, if I divide both sides by N2 as well, this will cancel out. What I'm doing here is I'm eliminating everything on the right side. So I have sine over cosine, which is nothing but the tangent of theta. And what I have surviving on the left side is basically mg times 1/2 over n2. Okay, so let's do that. So it's mg times 1/2 over n2. But going back and remembering that n2 is mu s mg, I can come back and rewrite n2 as mu s mg, which means that mg and mg can cancel out completely. And all I have here is basically 1 over 0.5. So, sorry, it's 0.5 at the top. So it's 0.5 over mu s, which is then 0.4. That means my tangent of theta is 0.5 over 0.4, which is 1.25. So tangent of theta equals 1.25. So for theta from that, we get 51 degrees. That means this is basically the minimum, right? This minimum angle it can have in order for the ladder to not start slipping. So that's the minimum angle that we can have, which is theta minimum is 51 degrees.